Good morning. My name is Dr. Ronald Tehini, and I'm going to give you a lecture about group theory. So that's my email in case you want to contact me for any question. Now, we will see the table of contents of this lecture. So the first chapter will be an introduction about group theory, where we will review the founding principle of this theory and the basic definition. And chapter 2 will be about the representation theory that will allow us to determine what we call the character table. This character table will allow us to deduce important property for given groups. And now in chapter 3 we will see the application of group theory to quantum physics, and in the chapter 4 we will see the application of group theory to molecular spectroscopy, and especially to vibrational spectroscopy, Raman and infrared spectroscopy. Now in chapter 5 we will see the application of group theory to solid state physics. Now, a few references. So there is several books about group theory. So there is books that are more mathematical, and there are books that are more about physics and books that are more about chemistry. So one good book that I use for the first 3 chapters would be The Group Theory Application to Quantum Mechanics by Paul H. Mayer. And now, as for the application of the group theory for molecular spectroscopy and quantum chemistry, etc., there are several books for that. Okay, so for example, this is one of the books in French. So, in this first chapter, like I said, I will introduce the basic definition and the founding principle of this theory. So, first of all, what is group theory? So, group theory is a mathematical theory, the base, that study algebraic structure called groups. So, group theory have important application in physics, in chemistry, in material, where in this case the elements of the groups are symmetry operations. So some fields of application of group theory, for example in quantum physics, okay, the group that we will study is the group of the symmetry of the Hamiltonian. So the operations of symmetry that leave the Hamiltonian invariant, and this can allow us to determine selection rules, for example, and the symmetry of the wave functions and other properties. Now, group theory is also used in quantum information, where they make extensive use of group theory, and they use Pauli group, Clifford groups, etc. And also the comprehension of the standard model in the physics of particle requires some basic notions of group theory. So one of the most important application would be the molecular spectroscopy and quantum chemistry and the construction of molecular electronic orbitals also, like we will see. And now group theory is used also in cryptography. And now a new domain of application of group theory is artificial intelligence. So it is used also in computer vision and robotics. So this is new applications of group theory, some new article of research, okay, in this domain use group theory. So, for example, an example of application in molecular physics, the group theory permits to find what we call the symmetric adapted molecular orbital, or permits to express the molecular orbital as a linear combination of atomic orbitals of given symmetry. Okay? For example, when you understand group theory, you will be able to understand the orbital diagram for a given molecule. Now, another example of application of the group theory is in vibrational spectroscopy, where the group theory permits to determine the symmetry of the normal mode of vibration. For example, here, okay, the vibrational mode of H2O has two symmetry modes, two different symmetry modes. Okay, we'll see that in chapter 4. Okay, and also it permits the determination of the vibration coordinate, the normal vibration coordinate. This means the system of coordinate where the Hamiltonian takes a simple separable form. And also an application of the group theory, the most important, is the selection rule for electronic and vibrational and Raman spectroscopy. In addition, group theory gives not only the information about the selection rule, means if this transition from this state to this state is allowed or not, but also permit to predict the polarization of the Raman spectrum. Okay, for example, this here, this line is strongly polarized. It depends strongly on the polarization, and this can be explained by group theory. Also, the electric properties, the tensor of polarizability, etc., can be also the elements that are non-zero can be expressed by group theory. So, first of all, let's define what's a group. So, we call a group a set of elements, okay, that I will denote E, A, B, C, D, etc., with an associative law that I will note dot here, such as no matter what A, B, two elements of this set, okay, the product of A by B, by the law here, dot, okay, by this law, belongs to J. And another condition also is the existence of a neutral element. So a neutral element is an element that no matter what the element A belonging to the group J, E multiplied by A is equal to A multiplied by E is equal to A. Okay? So this is the neutral element. Now when I say multiply, it's not necessarily multiplication. Okay? What does it mean? It means that the product, the action of E on A, okay, using this law. And this law can be an addition, a multiplication, multiplication of matrices, or any other law. Okay. Now, the third condition is that no matter what element belonging to J, each element has to have an inverse. So no matter what A belong to J, there exists A minus 1 such A minus 1 multiplied by A is A minus 1 is equal to the identity or the neutral element. And the fourth condition is the associativity of the law. Okay, so a group is a set element and an associative law. So the set of elements alone, okay, is not a group. Now, the number of elements in a group is called the order of the group. We will note it small j here. Okay? So a group can have a finite number of elements or an infinite number of elements. Now, in the case where the number of elements is infinite, the group can be continuous or discrete. Continuous means that the element depends on a continuous variable. Okay, we'll see example about that. Now I will introduce some additional definition. So first I will define the order of an element. An element A of a finite group G is said to be of order n if A power n is equal to the identity or the neutral element. The minimum order of A, if A is different than the identity, is 2, and the maximum order is the order of the group. Why? Because if A belongs to the group, then A multiplied by A belongs to the group. Then A multiplied by A can be equal to identity. In the other case, A cube is maybe equal to an identity, etc., 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 till the maximum order an is equal to the identity. Okay, so the maximum order of an element is the order of the group. Now, in general, if you take two elements of a group, the action of A on B, or the product of A multiplied by B, is different than B multiplied by A. Now, if A multiplied by B is equal to B multiplied by A, the group is said to be abelian. It's an abelian group that possesses some special properties that we will see. Now, a group is said to be cyclic when it can be generated by a single element A. So, any element in the group can be expressed as A power n. So the group will be A squared, A cubed, etc., A power J, A power G is equal to identity. Why A power J is equal to identity? Because if, for example, A power cube is equal to identity, or A power n, okay, so this element will generate only these three elements. Okay, and not all the group. Now, a cyclic group is necessarily abelian because any element commute with its power. So now I will present the rearrangement theorem, which is an important theorem that we will use after. So basically, let's consider that we have a group G, okay, a finite group. So if I take an element A belong to G and I multiply A by G, in other words, I form the ensemble of elements A multiplied by E, A multiplied by A multiplied by B, A multiplied by C, etc. Then this ensemble of elements is the group itself, but in different order. But it doesn't matter because the group is defined as the ensemble of elements. The order is not important here. Okay, the permutation of the element is not important. Now, the proof of this theorem is quite easy because it's enough to show that when I make the product of A by any element, any two different elements of G, then I will generate at every time a new element, and at the end I will generate the group itself. So okay, so let's consider two elements A and B belong to G that are different from the identity, because if A is equal to identity, then E multiplied by my G is the group itself. This is evident. And if B is equal to the identity, then A multiplied by E is A. So if I take A multiplied by B, then A multiplied by B is different, is an element C that is different than A and B. Because if A multiplied by B is equal to A, then if I multiply here from this side by A minus 1, I get A minus 1, A multiplied by B is equal to the identity, means B equal to identity. Similarly, if A is multiplied by A multiplied by B is equal to B, then B minus 1 is equal to identity, then A is equal to the identity. Now if I consider a different element D that is different from A and B, if I make the product A multiplied by D, it's different than A multiplied by B. Okay? So these two elements will be different. Okay? Now, so how I prove that? Because if A multiplied by D is equal to A multiplied by B, then A minus 1 AD is equal A minus 1 AB, then B equals D. So every time when you multiply an element A by an element of B, you get at an element of G, you get at every time a different element, and at the end you generate the group itself. Now I will give some examples of groups. Okay, so the ensemble of elements A such A n equals 1 form a group that we note by Zn here, and this is a cyclic group. For example, for n equals 3, 1 exponential I2 pi over 3 exponential 4 I pi over 3 is, where I is the complex the complex number here, is a group. Okay, because if you take two elements, so when you multiply these two elements, you get the identity. When you multiply ei2 pi over 3 by itself, you get ei4 pi over 3. When you multiply ei4 pi over 3 by itself, you get ei2 pi over 3, etc. Okay, so this is a group, and this is a cyclic group. It can be generated by this element here, ei2 pi over 3. Now, if I consider the set of vector and the 3D space, okay, with the law of vector addition, now this forms a group. So no matter what vector belong to the ensemble of vector in the three-dimensional space, the sum of the two vectors is a vector, and then it belongs to this ensemble. Now the neutral element in this case is 0. U plus 0 is equals 0 plus u is equal to u. And the inverse of an element, in this case, is minus this vector. So u minus u is equal to 0, the neutral element. So this is an abelian group because u plus v is equal to v plus u. And it's infinite because we have an infinite number of vector, and continuous because the vector can take any value. Now, a question: does the set of natural numbers, integer, form a group if we consider the multiplication as a law? I want you to think about that for a few seconds. And the answer is no, because in this case, if we consider 1 over an element, okay, 1 over an integer, it's not an integer. So an element of this ensemble with the multiplication as low is not a group, because we cannot define an inverse for an integer. Okay. Now on the other side, if you consider the same ensemble of integer, but in this time the sign integer, okay, with the addition, it forms a group. Now the set of real numbers also form a group, okay, with the multiplication this time, because you can define the inverse of A in this case. And of course the natural element here is 1, and so this group is infinite and continuous order. While, for example, the group of signed integers with the multiplication form a group that is infinite but discrete, because you have discrete values of natural numbers. Now, if we consider the permutation of an object, okay, this also form a group that we noted as n, and the order of this group is n factorial. Okay? So a permutation, a given permutation of an object is denoted by 1 to n here for the first line, k1, k2, kn. This notation means that I put the k1 object in the first position, the k2 object in the second position, etc. So for example here, this permutation p1, okay, means that the second object, I placed it in the first position. Okay, the fourth object, I placed it in second position. The third object, I placed it in fourth position, and the first object in third position, etc. Okay. Now, the natural element of this group is, of course, when you do no permutation. Okay, so 1, 2 till n, 1, 2 till n. Now, if you want the inverse of a permutation, so it consists of making the inverse of the permutation, or bringing the permutation to the initial configuration 1, 2, 3, 4, 5. Okay, so there's an easy way to compute that, is that when you want p1 minus 1, for example, then you invert the line and then you order the columns. Okay, so if p1 is 1, 2, 3, 4, 5, 2, 4, 1, 3, 5, then p1 minus 1 is 2, 4, 1, 3, 5, 1, 2, 3, 4, 5. Because you start from this configuration and then you get this one at the end. Okay, now if you want to reorder it in the same the same convention, okay, then you just have to order the columns here. Okay, so you will order here. So the 1, 3 here, you will put it in the first position. Okay, the 2, 1 here will become in second position. Okay, the 3, 4 here. Okay, etc. Now, if I want to calculate the product of two permutation, so now if I want to evaluate the permutation 1 multiplied by the permutation 2, this means that I make the permutation 2 and then I make the permutation 1 on the permuted objects. So this is permutation 2, this is permutation 1. So the permutation 2 consists of putting, for example, the fifth object in first position. Now, when I make the permutation 1 act on it. So the permutation 1 puts the first position, the first object in third position. So this first object here will be in third position. Okay? And similarly, the object 4 here is in second position. And now when I make the permutation 1 act on it, so the object that was in second position, I will put it in first position. So the 4 will be in first position. And for the tree, it stays the same here. And here it consists of putting the tree in fourth position, so the tree will be in fourth position. Okay? And finally, the 1 will be in fifth position. Now, so the permutation P1 multiplied by the permutation P2 is 1, 2, 3, 4, 5, 4, 2, 5, 3, 1. Now, if I calculate P2 multiplied by P1, then I get 1, 2, 3, 4, 5, 5, 3, 1, 4, 2. So in general, P1 multiplied by P2 is different than P2 multiplied by P1. So the permutation group in general is not an abelian group, except for two objects. So an important type of group that are encountered in physics and materials is the point group. So a point group are groups whose elements are operation of symmetry, rotation, reflection, inversion, or improper rotation. Now, we will define in chapter 4 the inversion and the improper rotation. So the elements of the group are element of symmetry, leaving at least one point unchanged. I will give an example here of the group of symmetry of the equilateral triangle, which is the same group than the group of symmetry for the molecule NH3, for example. So this group of course contains a neutral element and two rotation of 2 pi over 3 and 4 pi over 3. So if I rotate the triangle by 2 pi over 3 around the axis passing through the center here, I don't change the triangle. And there is 3 reflection that we call sigma 1, sigma 2, and sigma 3. 3 reflection around the axis passing by each vertex. Now, for the NH3 molecule, it's the same operation of symmetry, except here it's in 3D. So you have here plane, reflection planes, and the C3, the two rotation of 2 pi over 3 and 4 pi over 3. Now, this rotation, a rotation of 2 pi over 3 in spectroscopic notation is called C3. And this group that contain here 6 elements is noted C3V. We will see why after. Okay? So these set of elements form a group. So now I will introduce the Cayley table, or the multiplication table of a group. So the Cayley table regroups all the possible results of the multiplication of the elements of the group 2 by 2. So, for example, at the intersection of this line and this column lies the product A multiplied by B. And an intersection of this line and this column lies the product B multiplied by A. So now, as an example, we will construct the Caley table for the symmetry group of the equilateral triangle. So as we saw before, this group contains 6 elements. So the first element is the neutral element, or a 2 pi rotation. Second element is a 2 pi over 3 rotation that we will denote by C3. So first, let's give an index to each of the vertices of the triangle. So we will note by 1 this vertex, by 2 this vertex, and by 3 this vertex. So a rotation of 2 pi over 3 brings the vertex 2 in position 1, the vertex 1 in position 3, and the vertex 3 in position 2. So basically, this is equivalent to a permutation 1, 2, 2, 3, 3, 1. And now a rotation of 4 pi over 3 is equivalent to 2 times a rotation of 2 pi over 3. So we can rotate further by 2 pi over 3 this configuration. So the vertex 3 will come in this position, which is the position of 1 initially. The vertex 2 will come in this position, which is the position of 3 initially. And the vertex 1 will come in the position 2. So it's 1, 3, 2, 1, 3, 2. So additionally, we have 3 refractions. The first reflection, sigma 1, around the axis passing through the first vertex. So this is equivalent to a permutation of the vertices 3 and 2. The reflection sigma 2 consists of permuting the vertices 1 and 3, and the reflection sigma 3, which is equivalent to a permutation of the vertices 1 and 2. And now if I want to draw the Caley table for the group of symmetry of equilateral triangle, so I will put in the first line here the elements of the group, and the second line the element of the group. Okay, so C3, the rotation of 2 pi over 3. The rotation of 4 pi over 3 is denoted as C3 square by applying 2 times a rotation of 2 pi over 3. Then sigma 1, sigma 2, and sigma 3, the reflections. Now, the first line and the first column are evident because E multiplied by any elements give me the element itself, or the element multiplied by E gives me the element itself. Now C3 multiplied by C3 is C3 square. C3 multiplied by C3 square is C3 cube, means the rotation of 2 pi, or the identity. And C3 square multiplied by C3 is the identity. C3 square multiplied by C3 square is the rotation of 8 pi over 3. If you subtract 2 pi, which is 6 pi over 3, then you get 2 pi over 3. So it's C3. Now, if I want to calculate C3 multiplied by sigma 1, for example, I can do it using the geometrical representation or using the product of the permutation in this case. Now, I will show you using the geometrical representation. So C3 multiplied by sigma 1 means that I apply first the reflection sigma 1 on the object, and then I rotate the object by C3. So first I apply sigma 1. Okay, so sigma 1, okay, inverts the vertices here 2 and 3. And then when we rotate by C3, okay, so we get sigma 2. This is sigma 2. It consists of inverting the vertices to a 3 and 1. Okay, the two stay the same. So C3 multiplied by sigma 1 is equal to sigma 2. Now similarly, if you multiply sigma 1 by C3, you get sigma 3. So you get different elements. So it's not an abelian group here. Okay? And by proceeding the same, you can calculate all the elements of the multiplication table. Now, an important remark is that you must have only one element per line and per column. Why? Due to the rearrangement theorem. So when you multiply one element by the group, you must generate the element but in the group itself, but in different order. Okay, so this is a fast check if your multiplication, your Cayley table is correct or not. Okay, you must have only one element per line and per column.